All right, question 10. Consider the following interconnection of DT-LTS systems with H1 of n and H2 of n. We want to find the Z transforms of H1 and H2, specify the region of convergence, compute H of Z, which is the Z transform of the overall system, sketch the polar zero plot, and then find out if it has a DT-FT. Now, H of n is a series connection of two systems, H1 and H2. So we know that that's convolution in the time domain, and then that corresponds in the Z domain to big H of Z equaling H1 of Z times H2 of Z. And I have a little note here. So if we have some signal X of n and that signal has the Z transform X of Z, then if we take that same signal and we delay it in time by some n sub naught, we're going to have a Z transform that's equal to Z to the n sub naught times X of Z, where this X of Z is the same as that X of Z. And one more thing, if we take the Z transform of the delta function, well, that's going to be equal to 1. So H1 of Z is two time delayed delta functions, right? So we take the Z transform of this, which is a delayed delta function. We're delaying it by 1. We have n sub naught equal to 1, so that gives us Z to the negative 1 times 1. We'll leave that off. And then the next one, that's minus. We have a delta function delayed by an n sub naught of 2, so that gives us Z to the negative 2. And there's H1 of n, or H1 of Z. Now for H2 of n, so H2 of n is equal to 1 over 2 n minus 1 times u of n plus 2. We want to make this look like this. We do that like this. We have n plus 2 minus 1 u of n plus 2. Keep working through it. That's going to give us 1 over 2 to the negative 3 power times 1 over 2 to the n plus 2 power times u of n plus 2. That means that we have an n sub naught equal to negative 2. And then that's going to give us, we have 1/2 to the negative 3rd power. So we have 8 times 1 over 2 n plus 2 u of n plus 2. And that gives us a Z transform equal to 8. Now we delay it by negative 2. So we have Z to the 2 power times 1 over 1 minus 1/2 Z to the negative 1. And you can get this last part right from your table. So there's H2. Let's rewrite that up here. The big H2 is going to be 8Z squared 1 over 1 minus 1/2 Z to the negative 1. Now, the region of convergence is we do not want these functions to blow up to infinity, right? Or that's where we have to be careful of that. So if we look at Z to the negative 1, well, that's equal to 1 over Z. And we don't want that equal to 0, right? And when does that happen? Well, that happens as Z goes to infinity. And for Z squared, it's the same thing pretty much. So we have the magnitude of Z cannot equal infinity there. Now for H2, we're going to have 1 minus 1/2 Z to negative 1. We don't want that to equal 0, right? So we can multiply everything by z. That'll give us z minus 1/2 equal to 0. And then we end up with the magnitude of z must be greater than 1/2. So our region of convergence on this one is z must be greater than 1/2. And there's h1 of z, there's h2 of z, and there's our regions of convergence. So now big H of z is equal to h1 times h2. So we will get, we'll have 8, and let's just write it like this, 8z squared times z to the negative 1 all over 1 minus 1/2 z to the negative 1 minus 8z squared z to the negative, z to the negative 2 all over 1 minus 1/2 z to the negative 1. And if we do a little bit of algebra here, what will we get? We'll get, let's keep this 8 way out here. We'll have z over 1 minus 1/2 z to the negative 1 minus 1 all over 1 minus 1/2 z to the negative 1. And this isn't the easiest thing to figure out our poles and zeros from, so we can combine it. We'll have 8z minus 1 all over 1 minus 1/2 z to the negative 1. And if we multiply every term by z, we get 8z z minus 1 all over z minus 1/2. Let me double check my math. All right, yeah, so that's all correct. Now, our regions of convergence are going to be where the two overlap, right? And we know we had, let me say one more thing about this one here. So we know it's greater than 1/2 because if we look here, this is like a right-sided type function like we had on the S-plane of Laplace, right? We're going towards the right. When we talk about the z-plane, we're on the unit circle. A right-sided function is going away from that circle. It's going away from the origin, right? So that's how we knew that this one here was a greater than rather than a less than. So these are our two poles, or these are our two regions of convergences, right? So we're going to have a pole right here at 1/2. Now let's talk about some zeros. And this is the unit circle. This other one here, this is the unit circle. So if we will get zeros whenever our numerator is a 0, right? So if we plugged in a 0 for z, well, we have 8 times 0 times something else, but that all becomes 0. So we know we have a 0 right here at the origin. And then also if we have a 1, right? 1 minus 1 would equal 0. So we have a numerator of 0, which means that our entire function turns to 0. So we have another 0 right there. And our region of convergence is everything outside of the circle with a radius of 1/2. So there's our pole 0 plot. Here's our transfer function h. And now does this have a discrete time Fourier transform? Does that exist for h of n? Well, we don't even know h of n, but we don't need to know h of n because we know that the pole 0 plot of h of z contains the unit circle, which means it's a stable transfer function, and therefore it does have a discrete time transform, a discrete time Fourier transform. So C is a yes because the PZ plot contains the unit circle. All right, I'll be back with the last video here soon. Thanks.